Hi, Math 30-2s. Welcome to Probability Lesson 4. Today we're going to discuss what are called independent and dependent events. So the notation that you see at the top of the page here, okay, this represents A and B, okay? So the events A and B, we'll talk about what that means and how we find them when we are given sets of information or tables, charts, those types of things, okay? So investigating what we call independent events. So one card is drawn from a deck of cards and is replaced. A second card is then drawn. Consider the following events. Okay, so it says A is the first card is a heart, and B is the action of a second card is a heart. So determine P of A. Remember the P in front of the A means determine the probability of A. Well, in a deck of cards, we know that each suit, there are 13 cards. Okay, out of a total of 52 cards. So 13 out of 52, which will reduce to 1/4. Okay, determine the probability of B. Okay, a second card that is drawn is a heart. Okay, but the key is in the write-up of the question. It says a card is drawn and then it is replaced. So when I pick that first card and it's a heart, it doesn't matter if it is or is not a heart, it's put back in the deck. So again, when I go for the second trial now and try and determine the probability of B, which is also a card being drawn, okay, it's going to be the exact same probability. Okay, it's like I'm starting over again. So it says the probability of event B does not depend on whether or not A has occurred. Therefore, A and B in this case are what we call independent events. Okay, so they give us a nice definition right underneath of that. Two events are independent if the knowledge that one event has occurred has no effect, okay, does nothing on or determining the probability of the other event occurring. Okay, so investigating dependent events. One card is drawn from a deck of cards and is not replaced this time. Okay, a second card is then drawn. Consider the following events. So it says determine the probability of A. The first card is going to be a heart. So again, same as the last question, 13 out of 52, which will reduce to 1/4. Okay. Now in B it says, why is it not possible to determine the probability of B? A second card is a heart. Well, okay, it depends on whether or not the first card was a heart, right? So it depends on whether, I'm just writing this out for you, okay, whether or not the first card was a heart. All right. So in this case, the probability of event B depends on whether or not A occurred. In this case, A and B are what we call dependent events. So B depends on, or the probability of B depends on if event A occurred or not. So again, nice definition of what dependent events are here. It says two events are dependent if the knowledge that one event has occurred changes the probability of the other event occurring. So what we're going to take a look at now is just determining whether or not two events are dependent or independent. Classify the following events as dependent or independent. Okay, the experiment is rolling a die and tossing a coin. So the first event is rolling a 2 on the die, and the second event is tossing tails on the coin. So in this case, these two events would be what we call independent, okay? So the second event, which is tossing tails on the coin, has nothing to do with whether or not I rolled a 2 on the first die. Okay, the next one, or the second one, the experiment is choosing two cards without replacement. Okay, so when you pull that first card, you're not putting it back in the pile. The first event is that the first card is a king, and the second event is the second card is a king. Well, this is going to be dependent, okay, because in this case, it depends on whether or not the first card was a king. It's going to affect the probability of the second selection of a king. Okay, because I take that card out, I'm now down to 51 cards, and I don't know whether or not the first card was a king or not. Now in C, the experiment is choosing two cards with replacement. Okay, so I pick a card, but then I put it back in the deck. The first event is that the first card is a king, and the second event is that the second card is a king. Well, in this case, it's independent, okay, because no matter what I select for my first card, I'm putting it back in the deck, and I start with a full deck again to try and pull out a king once more. Okay, so what we've discussed now, since we've taken a look at what dependent and independent events are, on the next page is what we call conditional probability. Okay, so it says, consider the scenario from the previous page. One card is drawn from a deck of cards and here's the key, is not replaced. Okay, so always a good idea to highlight that or make note of that as you move forward in your question. A second card is then drawn. Consider the following events. Okay, A is the first card is a heart, and B is the second card is a heart. So the probability of A occurring, okay, again, which is what the P of A stands for, the probability of A is 13 out of 52 or 1 out of 4. But the probability of B depends on whether or not A has occurred or did not occur. So we denote by saying the probability of B given that A occurred. Okay, so that's what this is right here that I'm circling in red. The probability of B given that A occurred. Okay, and they even tell you that. So we denote P, B of A, the conditional probability of the event B, given that A has occurred. So in this example, the probability of B, given that A occurred, so given that A happened, which is the first card was a heart, would be what? Well, now that we would be down to 12 cards that are hearts out of a total of 51 cards, okay, because the card I select is not put back, and we're saying given that A occurred, so I'm now down from 13 hearts down to 12. Okay, in the next little example here, what I'm circling in blue here, well, this will now be the probability of B given that A did not occur, okay? So that's what that A little prime or tick means, okay, not A. So probability of B given that not A. So what's the probability of B occurring? And B was a second heart is drawn, given that A card is heart, first card is a heart, did not happen. So I would now still have 13 hearts because they're saying the first card was not a heart, but I'm down to 51 cards, okay? Because remember, in this experiment or this scenario, I am not replacing whatever card I selected, okay? So those two notations are extremely important, okay? The probability of B given that A occurred and the probability of B given that A did not occur. Okay, so we're gonna do a little example here to see if we can understand all the notation we've seen so far. So it says a red die and a blue die are tossed. The outcomes are shown in the array, which is just the table to the right there. Consider the following two events. So A is going to be the sum of the dice is 10. So remember the sum is the answer when we add. And B is the number on each die is the same. So 1, 1, 2, 2, okay, etc. So list the outcomes of the sample space. So A, again, was the sum of the two dice is 10. So all we're going to have there, the only way we can get to 10 is a 4 and a 6. Okay, 5 and 5. Okay, and then I also have to go 6 and 4, okay, because I can change the 6 and the 4 on the two die. Okay, so that's a different combination in this sense. Now in B, they're saying you get the same number on both die. So that, again, like I started listing, that's 1, 1, 2, 2, okay, all the way up to 6, 6. Okay, so I'm just going to list them out here. Okay, so again, you have them in your notes, and we can refer to them here as we move forward in this question. Okay, so there are all of the sets of data. Now, 3 says what there, okay? So again, notation's important here. This is A and B, okay? So when we say and again, remember it has to belong to both groups. So what is the only set of numbers there that you see that belongs to A and B? Well, that is, okay, the 5, 5. Okay, that's the only one that belongs to A and B. Now, notice there was no P in front of that, so I'm not talking about the probability of that occurring, which we will now talk about in the following questions, but that was just A and B. So it's 5, 5. So you can see they start with what's the P in front of it, the probability of A occurring. Well, A, if you look at A that we listed, there's only 3 events there. Now in that array or that table, there's 36 total events, right? 6 down, 6 across. That's 36 total events. A has 3 events in it. So that's 3 events out of a total of 36. Okay, that can reduce divisible by 3 to 1 out of 12. Okay, so there's the probability of A. Okay, the probability of B, I take a look at B, there were 6 outcomes there out of, again, a total of 36. That can reduce to 1 over 6. Okay, now here's our new notation, the probability of B given that A occurred. Okay, so the probability of B given that A occurred. So the easiest way to do that for me is I look up at A and B that I've written the sets for, okay? So I want B to occur, okay? I want this to occur given that this occurred, okay? So A occurred, so basically you kind of deal with A like your framework. Okay, A occurred, and I'm looking for the B events inside of A. Okay, so I'm looking for any B events inside of A. Well, there's 1, the 5, 5. Okay, so the probability of B occurring given that A occurred first. So A occurred first, the 4, 6, 5, 5, 6, 4. Now what's the probability of finding an event B inside of those 3 sets in A? Well, there's only one, right? It's the 5, 5. So this is going to be 1 out of a total of 3 events, okay? Now, in 4, it goes the other way, okay? So now it's saying, what's the probability of A given that B occurred? So this time they're saying B occurred first, right? The probability of A happening given that B did happen. So B happened, okay, which is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. What's the probability I'm now going to see event A in B? Okay, so how many of A are in B? Well, again, that's just 1, but this time it's 1 out of 6. Okay, so 1 event from A is in the 6 that are listed under B. Okay, now next, what's the probability of A and B? Well, remember A and B was just 5, 5. That was the only event. Okay, so that's 1 event out of a total of 36 events in that whole array. Now B, what's the probability of B and A? Well, that's also going to be 1 out of 36. So in a case like this, it's important to note that A and B is going to be the same as B and A, right? Where they overlap, okay, those events, it's going to be the same, okay? So A and B is the same as B and A. Now, verify the following. So we're just going to use the probabilities that we did and multiply to see if we can make the left-hand side of these statements equal the right-hand side. So the left-hand side, the probability of A and B, okay, we just go up to the calculations we did there. The probability of A and B, that was 1 out of 36. So there's my left side. Now the probability of A, that was 1 out of 12. Okay, you can see that again in our calculations. And the probability of B, given that A occurred, was 1 out of 3. So when I multiply these together, I get 1 out of 36. And there you go. The left side equals the right side. Okay, so that statement is true. In the second one, the probability of B and A, okay, so that again, that calculation there was 1 out of 36. I just refer to the calculations up above. The probability of B, okay, we calculated that to be 1 out of 6. I'm going to multiply that by the probability of A, given that B occurred, that was also 1 out of 6. So again, on the right-hand side, now I do have 1 out of 36 again, and you can see those values satisfy the equation. The left side equals the right side. Okay, so that takes us to the next page, which is the multiplication law for dependent and independent events. Okay, these again are going to be on your formula sheet, but not listed with a title. So when you go and you're using your formula sheet, you want to make sure you are aware of which formula is which, okay? So this one is the multiplication law for dependent events, and you can see it's the probability of A and B equals the probability of A times the probability of B given that A occurred, okay? So I'm just reading through this formula right there. Okay, now we're going to practice using that. 2 cards are drawn without replacement, okay, from a standard deck of 52 cards. Determine the probability of the following events. Both cards are red. Well, the first card being red is 26 out of 52, right? Half of the deck is red. Now, without replacement, but it's the probability of B now, given that A occurred. So again, it's the probability of a red card given that I did get a red card. So that means my total number of red cards drops to 25, and the total number of cards in the deck drops to 51 because I'm not replacing those values. So, okay, I multiply the 26 by 25, the 52 by 51, and then reduce that fraction, okay, and I get to 25 all over 102, okay? Now in B, it says neither card is a club, okay? So how many cards are not clubs? Well, that's 39 out of 52. How many cards are not clubs? 39 out of 52. So there's the event A, okay? Not a club, okay? So we also want the second one is not a club, okay? Given that the first one was not a club, okay? So now 38 and out of 51, okay? So we're gonna go 39 times 38, okay, times 52 over 50, or 52 times 51, okay? Reduce that fraction, and that is 19 out of 34. Okay, third example. The first card is a king, and the second card is a 5. So the first card is a king. Well, there are 4 kings out of 52 cards in the deck. Okay, now what's the probability of getting a 5 given that I got a king in the first one? Well, that doesn't change how many 5s are there. There's still 4 5s in the whole deck, but the total number of cards now drops to 51. Okay, so that's going to be 16 over 52 times 51. Okay, reduce that, and you get 4 all over 663. All right. Last one here for this section. One of the cards is a king and the other is a 5. Now, notice it doesn't say, like in C, the first card is and then the second card is. You just have to have one card that's a king and one that's a 5. So you kind of have two options here. You could have a king and a 5, or, okay, remember what does or mean? It means we're going to add, or a 5 in the first card and then a king in the second one. Okay, that satisfies the question because, again, it doesn't say the first card has to be and the second card has to be. So if I deal with the king and then the 5, well, that's going to be 4 out of 52, right? 4 kings out of 52, and then 4 5s out of now 51 cards. Or, okay, it's going to be the same calculation here, isn't it? 4 out of 52, and then 4 over 51, okay? So basically, one of those calculations then multiplied by 2, okay? So multiply 16 over, we just did that in the last question, okay, times 2, and then reduce that, okay? So we are now going to get 8 all over 663. Okay, now we take a look at the multiplication law for independent events, okay? So it says if the events A and B are independent, then the knowledge that A has occurred has no effect on the probability of B occurring. This means the probability of B given that A is just the probability of B, okay? So we just go the probability of A and B is simply the probability of A times the probability of B. 2 cards are drawn with replacement. So whatever you select, you put it back in the deck, okay, when you're going to draw the second card. From a standard deck of 52 cards. Determine the probability of the following events. Both cards are red. Okay, well, again, the first card would have a probability of 26 out of 52. Now, whether or not that happens, okay, you put that card back in the deck. So again, your probability for the second selection is, again, 26 out of 52. Okay, multiply those together, okay, and reduce that fraction to 1 over 4. Okay, in B, the first card, so again, now they're telling you the order. The first card is a king, and the second card is a 5, so it's in that order. So the first card being a king, that's going to be 4 out of 52. Okay, and again, whatever that card is, I put it back. So now the second card is a 5. Well, there's still 4, but again, this is out of 52 again. So multiply those together, okay, and reduce. Okay, so 1 over 169. Okay, one of the cards is a king and the other is a 5. So again, they do not talk about the order in which the cards have to be selected here. So just like up above, this could be a king, then a 5, or a 5, then a king. So when I do this calculation, it's going to be 4 out of 52 for the king. Put that card back. So again, 4 out of 52 once more. Or, so I'm going to add this calculation, 4 5s out of 52 total cards. I put whatever card I select back. 4 kings out of, again, 52 cards. Okay, so I'm going to add those together. Okay, and it's going to be the calculation from B twice. So I'm going to get 2 all over 169. All right, so there's your dependent and independent formulas. Okay, make sure you write down on your formula sheet which is which so that when you refer to them during a test, a quiz, any of those things, you know what is what. Now, students often confuse the concept of mutually exclusive events with the concept of independent events. These terms do not mean the same thing. So this whole section here is really important. The concept of mutually exclusive events involves whether or not 2 events can occur at the same time. Okay, so mutually exclusive events we're talking about, can they happen at the same time? When we talk about independent or dependent event, it involves whether or not the occurrence of one event affects the probability of the other event occurring. So with independent and dependent events, we're talking about one event occurring and then another one happening after. With mutually exclusive events, we're talking about can they happen at the same time. So let's take a look at some questions here that deal with those types of statements and those terms. Now, in class example 4, it reads like this. If the probability of A is 1 out of 3, the probability of B is 2 over 5, and the probability of A or B is 3 over 5. Use appropriate formulas to investigate whether event A and B are mutually exclusive and then B independent. Well, if I'm talking about mutually exclusive events, okay, I refer back to my mutually exclusive formula, okay? So what I'm going to do, and they've given me the nice pieces of the puzzle here, I'm going to go the probability of A plus the probability of B. Okay, I'm going to add those together. So this is going to be 1 out of 3 plus the 2 over 5. Okay, find a common denominator, which would be 15. Okay, so that's going to be 5, 6. So that's going to be 11 over 15. Okay, so there's the probability of A plus the probability of B. Now, I want to take the probability of A or B, okay, which is the other side of that equation, okay, and they've given that to me. That's 3 out of 5. That's in the write-up of the question, okay, so I don't have to do any calculation there. I just copy it from up above. Now, you take a look at those two calculations, and I'm going to say, well, the probability of A or B, okay, does not equal the probability of A plus the probability of B. Okay, that's just a formula from my formula sheet, which deals with mutually exclusive events, okay? So, therefore, okay, A and B are not mutually exclusive, okay? And that just comes from the formula, okay, and filling in the values that I know, and away we go. Now, okay, it says for B, are event A and event B independent events? Well, since I know from A, okay, that the events are not mutually exclusive, okay, right here, they are not mutually exclusive, I use the non-mutually exclusive formula in B, okay? So I start by using the non-mutually exclusive formula in B, which looks like this. The probability of A or B, okay, equals the probability of A plus the probability of B minus the probability of A and B. Okay, so again, that's from our formula sheet. Okay, so I use the not mutually exclusive formula from the formula sheet. So if I take that formula now, okay, I'm going to rearrange it so that I can solve for the probability of A and B. Okay, this is what I'm after. So you'll see why in a second here. So I'm going to take that to the other side of the equation. So now this is the probability of A and B. And that will become the probability of A plus the probability of B minus the probability of A or B, okay? So when I fill those values in, the probability of A, okay, that was 1 out of 3, plus the probability of B, that's 2 over 5, okay, and the probability of A or B, which again comes from the write-up of the question, is 3 over 5, okay? So on the right-hand side, okay, what I get here when I add 1 over 3 plus 2 over 5 minus 3 over 5, okay, common denominator, okay, this is going to give me 2 out of 15. So that's the probability of A and B, okay, so the probability of A and B is 2 over 15. Now, when I go the probability of A times the probability of B, okay, I'm going to multiply those together. So that's going to be 1 over 3 times 2 over 5. So this will be 2 over 15. Okay, well, what do you know, right? So if I take a look at my formula for independent and dependent events, this is what I've just shown with my calculations. I just showed that the probability of A and B, okay, that was 2 over 15, equals the probability of A times the probability of B, okay? That was what I've calculated right there. So if you take a look at your formula sheets, what did I just prove? Well, if the probability of A and B equals the probability of A times the probability of B, I can therefore state that A and B, okay, are independent, okay, which is what they asked me to figure out here. Okay, so I'm just going to write that on the side. So having a good grasp of those formulas, you guys, for probability and labeling what each of them does or how we can use them is really important, okay? Next, let A and B be events with the probability of A being 1/2, probability of B being 1 over 3, and the probability of A and B equaling 1 over 4. So determine, now you have to know your notation here. In A, it says the probability of B, given that A occurred, In B, the probability of A given that B occurred, and then in C, the probability of A or B. Okay, so the first one, the probability of B given that A occurred. Okay, so what I'm going to do is I'm going to find those on my formula sheet. Okay, the probability of B given that A occurred, and what you'll see is that I find it in this formula on my formula sheet. So the probability of A and B is equal to the probability of A times the probability of B given that A has occurred. Okay, we learned that formula today, didn't we? And what are we after in that formula? Okay, we are after this piece of the formula right there that I've triply underlined. Okay, so you can do it once you substitute the numbers in, or, okay, you can rearrange the formula first, but that's what I'm after there. So you'll see, okay, that what I have here is the following. The probability of A and B, okay, given from the write-up of the question, that's 1/4, okay? The probability of A is 1/2, okay? And that's going to be times the probability of B given that A occurred. That's what I'm after. So what do? Well, right now on the right-hand side, I'm multiplying by 1/2. So I'm going to divide both sides by 1/2, okay? So you're going to end up with 1/4. You're going to divide by 1/2. That will equal the probability of B given that A has occurred. And we know with our fractions that this is 1/4 times 2/1. Okay, that will be that probability of B given that A occurred. So that's going to be 2/4, which is 1/2. Okay, so there's 1/2, the probability of B given that A has occurred. When I go to B, okay, what you'll notice in B is that it's going to be very similar to what we did in A. It's just that the A and the B are switched, okay, between this formula. So all I do is I go to the same formula I used, and I switch the letters. So instead of it being the probability of A and B, it's going to be the probability of B and A will equal the probability of B times the probability of A given that B has occurred. Okay, so I follow that same formula. Okay, now we are after the probability of A given that B occurred. Well, we learned early on today that the probability of B and A is the same as the probability of A and B. Okay, so that's going to be 1/4. Okay, we learned that in that 2-die question. Okay, remember the probability of A and B, the probability of B and A, they were the same calculation. So then the probability of B, well, this is 1/3, and times the probability of A given that B has occurred. That's what I'm after. So again, just like in the last question, I'm now going to go 1/4 divided by 1/3 because I'm multiplying by 1/3 on the right-hand side of the equation. Okay, that will isolate the probability of A given that B occurred. So this becomes 1/4 times 3/1, okay, which will give me my calculation I'm after. Okay, and this will end up being 3/4. So it's 3/4 is equal to the probability of A given that B has occurred. All right. So now the last question that we're going to take a look at here is the probability of A or B. Okay, so based on what we've learned here, okay, we can now use the formula, the probability of A or B, okay, that is what we are after, equals the probability of A plus the probability of B minus the probability of A and B. Okay, so we've got all those pieces of the formula. The probability of A, 1/2, the probability of B, 1/3, minus 1/4, which is the probability of A and B. Okay, we need a common denominator here, which will be 12. Okay, so if you add all of those values together over a common denominator of 12, you will get 7/12. Okay, and there's your probability. So let's get into some word problems here and see how we are going to answer these. The probability that Sophia will pass math this semester is 0.7, and the probability that she will pass English this semester is 0.9. If these events are independent, okay, so that's probably something pretty important that we need to underline. Determine the probability to the nearest hundredth. So this time they don't want fractions, they want decimals to 2 places that she will pass math and English. Now, so we know that math and English, okay, and they've already told me in the question that these events are going to be independent. So math and English is going to be like M and E. I'll use those letters, okay, to represent math and English. You can use A and B just like we do in all the formulas if that's easier for you to follow. But because of this question, I'm just going to write it like this. The probability of math and English, okay? And again, if you don't like that, use A and B, where A is math and B is English. So when I follow the formula, because I know that they are independent, this is just the probability of passing math times the probability of passing English, okay? And it's because that she will pass, okay? Not that she will fail, but that she will pass. So this is going to be 0.7 times English, which is 0.9. Okay, multiply those together, that'll be 0.63. Okay, now this is math or English. So are these events, when we're using or, are these events mutually exclusive? Okay, so these events are not mutually exclusive. Okay, so then I go to my formula sheet, and because I'm smart, I've labeled which formula is not mutually exclusive, and this is going to be the probability of math, and then we say or English, okay, which using the not mutually exclusive formula is the probability of math plus the probability of English, okay, minus the probability of math and English, okay? And again, if you're using A and B, you just replace the M's with A's and the E's with B's, okay? And you can follow that same formula. So now I do my calculations, 0.7 plus 0.9 minus, now the probability of M and E, I just did that in the last question. That's 0.63, okay? So add them together, okay? Subtract, and you get 0.97. Okay, in C, math, but not English. So how would I notate that? Well, again, these are independent events. Okay, so this is going to look like this: the probability of math and not English, right? Remember the little prime tick by it means not. So what is that going to be? Well, because they're independent, it's just the multiplication of those two probabilities. So the probability of math times the probability of not English. So the probability of passing math, that was 0.7. Now the probability of not passing English is going to be 0.1. Why? Because the probability of passing was 0.9. Okay, so 0.1 is going to be the probability of not passing English. Remember, probabilities of an event are always going to add up to 1 or 100%. So that's how I get the 0.1 or 10%. So multiply those together and you get 0.07. Okay. Now in D, neither math nor English. Okay, neither math nor English. Okay, so that's like saying passing, not math, and not English. Okay, so that's the same way of notating. Well, again, if they are independent events, okay, which they are, it's just going to be the probability of not math times the probability of not English. So passing math is 0.7, not passing math, 0.3. Passing English, 0.9, not passing English, 0.1. Okay, so multiply those together, 0.03. Okay, so again, you need to classify the calculation you're doing first, and that will help you find the formula, okay, that you need on your sheet and how to apply it. All right, last example for today, you guys. A number is selected from the first 10 natural numbers, okay? Remember, natural numbers start at 1, okay, and their whole numbers moving forward are in the positive direction. Consider the event M, which is a prime number is chosen, and event N will be an odd number is chosen. List the sample space for the outcomes M, N, M and N, and M or N. Okay, so they want all of those sample spaces, okay? So the universal set here, okay, I'm just going to write this out. So the set of all the natural numbers that I'm picking from are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so they said the first 10 natural numbers. So there's kind of the universal set, all the numbers I can pick from. Now, they want event M. Well, what is event M? Okay, a prime number is chosen. So remember, prime number is divisible only by 1 in itself. So 1 is neither prime nor composite. So 2 is the first prime number, 3 is prime, 5 is prime, and 7 is prime. Those are the only numbers that are divisible by 1 in itself. Event N, okay, so what was event N? Go to the top. An odd number is chosen. So list all the odd numbers in that set S. That's 1, 3, 5, 7, 9. Okay, now we move on to M and N. So they want event M and N. So what are the events that belong to M and N in both of the blue and the red set? Well, that's a 3, a 5, and a 7. Okay, so there are the events in M and N. Now M or N, okay, remember or is inclusive, okay, so that means it can belong to one set or the other, okay, or both. So that's going to be 1, 2, 3, 5, 7, 9. Basically, I write out all the numbers that are in either of those sets. Okay, so there is just the sample space for those sets. Now they want the probabilities, okay? So when I go and I write this out, what's the probability of M? So I take a look at M, and there are 4 events in M, right? I'm focused right here, M. 2, 3, 5, and 7. Well, that's 4 events out of 10 numbers, right? Because there were 10 natural numbers, the first 10. So 4 out of 10 reduces to 2 out of 5, okay? The probability of N, okay? So now we move on, and I set my sights on event N, okay, which is right here. So there's 5 events there. So 5 numbers out of the first 10 natural numbers, that will reduce to 1/2. Okay, now the probability of M and N. Okay, so now, okay, you move on and you take a look at M and N. That's right here. That's 3 numbers out of the 10. Okay, you can't reduce that. And then lastly, the probability of M or N. Okay, take a look at that list, okay, which is the one just below M and N. So that's right here. And that's 1, 2, 3, 4, 5. That's 6 numbers, okay, out of the first 10 natural numbers. That will reduce to 3 out of 5. Okay. C now says, determine P, a prime number is chosen, and then there's the line, given that an odd number is chosen, okay, which is, they notate like this, and that's correctly, okay, give the probability of M given that N occurred using an appropriate formula, okay. So we can use the formula and rearrange it like we did in class example 5 on the last page, okay. So if you take a look at class example 5 on the last page, okay, we can do it that way, but there's a quicker way, okay? Remember, when I take a look at this, and I showed you this with the die question, this is saying the probability of M given that N occurred. So when I do that, I'm looking for the elements of M inside of N, because I want to find M given that N occurred. So you kind of work backwards. You say, okay, N occurred. So if N occurs, those are the numbers 1, 3, 5, 7, 9. Okay, that occurred. Now I'm looking for M inside of N. Well, what is M? A 2, it's not there. The 3 is there, okay? The 5 is there, and the 7 is there. So there are 3 numbers I circled out of a total of 5. So there's the probability. So the probability of M, given that N occurred, is 3 out of 5, okay? So that's kind of how we do that, okay? So when you read that, the probability of M given that N occurred, so N occurred, write down those elements, the 1, 3, 5, 7, 9. Now, what's the probability of finding M inside of N? Okay, so the M were the 2, 3, 5, 7. I only see the 3, 5, 7. That's 3 numbers out of a total of 5. So the probability is just 3 out of 5. If you prefer, you can follow the same kind of calculation we did in class examples, class example 5, A and B. Okay, same idea where you kind of rearrange the formula to find or isolate the probability of M given that N occurred. Aiden said that a quicker method for determining the answer in C would be to look at the number of odd numbers in the sample space and count how many of these were prime. Do you agree? Well, of course I do, yes, because that is exactly what I just did. So this, D, is exactly what I just did here. I didn't use the formula, okay? I just used that logic right there. So now, they want us to do the same thing. This is determine an odd number is chosen given a prime number is chosen, okay? So this time, what you're really looking for is the probability of N given that M has occurred. Okay, so let's do the same thing I did last time. I want to find N, but inside of M. So given that M occurred, so what were the M values? The M values were 2, 3, 5, and 7. So that occurred. Now what's the probability I find N, which is 1, 3, 5, 7, 9, inside of there? There's no 1, there's a 3, right? There's a 5, there's a 7, there's no 9. So I just circled 3 numbers out of the 4 that I listed. So the probability of N, given that M occurs, is 3 out of 4. Okay, and that's it. So again, really, really important that we go to our formula sheets, okay, or wherever we're referring to our formulas, and write down what each formula okay, is specific for, and that will help us a lot when we go through these questions. Again, we need to know the difference, as we did at the top of page 150, the difference between when we're discussing mutually exclusive events and when we're discussing independent and dependent events. Okay, any questions, you guys, please email them to me. I'll get back to you with some helpful hints or calculations, and also take a look at the Google Classroom. Okay, I've posted a date for your test regarding this chapter. All right, have a good night. Talk to you soon.